Hi everyone, so today we're going to talk about complex numbers in polar form. So this is essentially the conversion of a complex number in the form of x plus iy to its polar form. Now the polar form is usually easier to deal with. In most of the trickier questions or the questions that seem a little bit weird, a little bit challenging, they usually involve complex numbers in the polar form rather than in standard x plus iy form, right? And then we're also going to talk about Euler's identity, which many people consider the most beautiful equation in mathematics. Now, Euler, this guy is absolutely a genius, right? He's done work in pretty much all the fields of mathematics, graph theory, number theory, complex numbers, algebra as well. So we're going to learn his Euler's identity for complex numbers, right? So let's just get right into this. This is the problem number 22 from the AMC 12A in the year 2020. And in this video, we're going to talk about how complex numbers look in polar form. So we've talked about a little bit of the complex numbers in its standard form x plus iy, but we're going to see how we can convert any complex number in the form x plus iy to its polar form, right? So we're going to involve theta and our polar coordinates a little bit, right? And then we have Euler's identity for complex numbers, a really fascinating equation. Then we're also going to at the very end talk a little bit about infinite geometric progressions, and obviously we have book suggestions for AMC 1012 and a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so they're saying for I is equal to square root of minus 1. So standard iota, we're dealing with complex numbers, and n is a natural number. Define real sequences an and bn by this expansion, right? 2 plus I raised power n is equal to an plus I times bn, and evaluate this infinite looking sum, right? So before we get into this, let me just introduce you to the Euler's identity, right? Euler's identity for complex numbers, or Euler's theorem for complex numbers. So it essentially states that e raised to the power I theta is cosine theta plus I sine theta. You might have seen this before. And if you actually plug in theta is equal to pi is obviously radians, you'll get e raised to the power I pi is equal to cosine pi, which is minus 1, plus I sine pi, but sine pi is equal to 0. So e raised to the power I pi is equal to minus 1. And we get this very famous result, right? E is a transcendental number, I is a complex number, pi is obviously irrational, and when you exponent these quantities, you actually get an integer. Quite fascinating. Transcendental numbers, complex numbers, irrational, and then you have this minus 1, right? It's quite interesting. But okay, that aside, you must know this Euler's identity. It's one of the most well-used expressions in complex numbers. Okay, so now that is done, let's just discuss how these complex numbers look in the polar form, like I was referring to earlier. So let's just maybe discuss a little bit about polar coordinates first, okay? Polar coordinates. So let's just consider a standard Argand plane. For example, this is the x-axis, this is the y-axis, right? Let's just consider the standard coordinate plane, right? So any point over here can be represented as x comma y, right? Okay, awesome. But there's actually another way to represent this. And that representation is in terms of its distance from the origin, which I'll call r, and this angle theta. So from basic vectors or basic trigonometry, you'll actually notice that x is actually r cosine theta. Just basic trigonometry, find out this distance x. And similarly, this perpendicular will be y. So y is effectively r sine theta. So basically, x comma y can in a way be represented as r cosine theta and r sine theta, right? Isn't that cool? It indeed is, right? Now, if we talk about the complex plane, so if we talk about the Argand plane, so this will be real and this will be complex. So obviously any point over here will again be represented as x plus iy. So for example, we will have z x plus iy, where this is, let's say, x, this is, let's say, y. Now again, there's another way to represent this. So this essentially becomes, again, x is equal to r cosine theta, y is equal to r sine theta. Let me just make its diagram a little bit so it'll be more clear. This is r and this is theta. Now from the fundamental of complex numbers, we know that the r is nothing but the distance from the origin to the complex numbers. So this is really nothing but the modulus of the complex number z. Now z is equal to x plus iy. So if I just replace x is equal to r cosine theta and y is equal to r sine theta over here, I'll get something like this. Correct. Now I can take the r common, and over here I'll get cosine theta plus I sine theta. Now what was r? R was the modulus of this complex number z, and cosine theta plus I sine theta is e raised power I theta. So do you notice what we've done here? We've taken any complex number z and we've converted it into this form, which is called as the polar form. Right? So effectively, x plus iy can be represented as the modulus of the complex number z will be nothing but the square root of x square plus y square times e raised power I theta. Okay, where theta is this angle like we talked about. Right? Okay, that's awesome. So in the question, they had given us a complex number already, right? They had given us 2 plus I, and our entire scope of discussion is going to be limited in a way to this number 2 plus I. So 2 plus I can be represented as, well, what will be the modulus? Square root of 4 plus 1, so that becomes 5 root 5 e raised power I theta. And let me just represent this on the Argand plane so that you get a better idea. This is obviously a real, and this is our complex axis. So this is, let's say, point number 2, this is point number 1. So this will be our complex number z, 2 plus iota. And this is obviously going to be theta, and it's easy to see that tan theta, well, perpendicular upon base, is nothing but 1 over 2, as the height is clearly equal to 1. Now similarly, using elementary trigonometry, I can state that cos theta is equal to 2 by root 5, as the hypotenuse is root 5, or in other words the modulus is root 5, and sine theta becomes 1 by root 5. So maybe keep these values in the back of your mind because we are going to need them sooner or later. But effectively, for the time being, you must remember this. You must this is the important result for us, right? 2 plus I converted into its polar form. That becomes root 5 times e raised power I theta. So now I hope that you can really convert any complex number into its polar form using this simple equation, right? Okay, perfect. So now that we have this, well, in the question they were raising this to the power n. So let's just also raise this to the power n. Right, and then you will get root 5 raised power n times e raised power I n theta. Now, e raised power I theta was cosine theta plus I sine theta. Now, in a way, e raised power I times n theta will be theta replaced with n theta. So, cosine n theta plus I sine n theta. So, basically, when I use this over here, I'll get 2 plus I raised to the power n is equal to root 5 raised to the power n times cosine n theta plus I sine n theta. And really this thing 2 plus I raised power n, they are represented as a n plus I times bn. So it's clear to see that a n becomes root 5 raised power n times cosine n theta, and bn becomes root 5 raised power n times sine n theta. So now that we've established that, now things are probably a little bit easier to deal with. So now we really just want to find the sum. Right? Essentially, at the end of the day, we want to evaluate the sum, and the sum was summation from n is equal to 0 to infinity. It's an infinite sum of a n b n divided by 7 raised to the power n. So let's just plug in these two quantities out here in this sum, and let's see what we get. So when you do this, you will get s is equal to summation from n is equal to 0 to infinity of 5 by 7 raised to the power n, and this becomes cosine n theta times sine n theta. Now what I'm going to do is I'm going to multiply by 2 and divide by 2. So I can take this 1 by 2 outside over here. So sum becomes 1 by 2 summation from n is equal to 0 to infinity of 5 by 7 raised to the power n, and this really becomes sine of 2 n theta, because sine 2 theta is equal to 2 sine theta cos theta. And really, to convert this into sine 2 n theta, I just multiply and divide by 2. It's a standard manipulation that we do in trigonometry, very standard. Right? And over here, if you just replace theta with 2 n theta, you'll see the expression that we have essentially obtained. Okay, great. Now there's a little bit of an observation. So e raised to the power I times 2 n theta. What will it be? By Euler's identity, I'll know that this will be cosine 2 n theta plus I sine 2 n theta. So can I write sine 2 n theta, which by the way we have here as well, as the imaginary part of e raised power I times 2 n theta? I mean, of course I can, right? Because the imaginary part is this and the real part is this. So sine 2 n theta, which we have over here, is really nothing but the imaginary part of this quantity. So I can write the sum s as half times summation from n is equal to 0 to infinity of 5 by 7 raised to the power n times the imaginary part of e raised to power I times 2n theta. Okay, amazing. So I can take everything inside this imaginary part. So this becomes imaginary part of 5 by 7 raised to power n times e raised to power I times 2n theta. Okay, awesome. Now then that's like an interesting result. The sum of the imaginary parts is actually equal to the imaginary parts of the sum. So whenever you have summation of an imaginary part, you can swap the summation and the imaginary parts, and it will still be the same expression. So I can essentially take this imaginary part over here and can send the summation inside, n is equal to 0 to infinity of 5 by 7 raised to the power n times e raised to the power I times 2n theta. And this obviously entire thing is in the summation. Now it's clear to see that this is a very standard geometric progression, and the infinite sum of a geometric progression is a over 1 minus r, where a is the first term and r is the common difference. So in this case, sum becomes half times the imaginary quantity. A will be the first term, just plug n is equal to 0, you'll get 1. So 1 divided by 1 minus common ratio, which is 5 by 7 times e raised to power 2I theta. Right, you plug in n is equal to 1 basically. Okay, so we've reached till that. Now we've essentially found a little bit of a closed form for this sum s. Now we don't have to deal with summations. The summation, entire thing is done. We just need to calculate the imaginary part of this quantity, this weird looking expression that we have in the bracket. So e raised to power I theta is cosine theta plus I sine theta. But in our case, like I said before, cosine theta was 2 by root 5 and sine theta is 1 by root 5. Right? Remember I told you to put these values in the back of your brain because you're going to need that later. And this essentially comes from the fact that we are considering the complex number z is equal to 2 plus I. So for this complex number, cosine theta is 2 by root 5 and sine theta is 1 by root 5. So basically, e raised to power I theta is 2 by root 5 plus I times 1 by root 5. So e raised to power 2 I theta will be nothing but just square this quantity. So I just square on both sides, and then I square on both sides, I'll get 3 by 5 plus 4I by 5. So e raised to power 2I theta, which was needed over here, I'm just going to replace that and let's see what we get. So we get the sum s is equal to half times the imaginary part of 1 divided by 1 minus 5 by 7. And over here you have 3 by 5 plus 4I by 5. So it's clear to see that these 5 and 5 get cancelled out. So sum becomes half of the imaginary quantity, 1 divided by 1 minus 3 by 7 plus 4I by 7. Right? So the sum becomes half times the imaginary quantity of, well, you can just take the 7 over here and just simplify this a little bit. So you'll get 4 minus 4I. Now, once you've reached this, at this point, we can just rationalize it a little bit and then we would be done, right? This becomes half times the imaginary part of 7. This becomes 4 plus 4I. This becomes 4 minus 4I times 4 plus 4I, right? And now this becomes sum is half of the imaginary part of 28 plus 32I. This becomes 16 plus 16 as I square is negative 1. So this just becomes how much? 32. I beg your pardon. This will also be 28, of course. 7 times 4 is 28. So sum is half times the imaginary part of 28 by 32 plus 28I by 32. But what is the imaginary part of this expression? It's obviously 28 by 32, right? The coefficient of this I is always the imaginary part. So the sum is nothing but half times 28 by 32. If I just simplify this a little bit, this is 14, this is 7, this is 16. So the sum is indeed 7 by 16, and that is our answer. So yeah, it was quite an interesting question, and like we've seen in many questions before, when we have complex numbers in its polar form, it's actually easier to deal with. It's actually easier to do some of the more complicated looking expressions, because really you would have done this by binomials also, but it would have been really messy, really complicated, and that's really an unnecessary way to do this, right? Because you could have expanded maybe 2 plus I raised per n using a little bit of binomials, but then again, that's really not a very efficient way to do this. And conversion into polar form made a lot more sense, and therefore when we're usually dealing with exponents, things are a lot easy, right? Exponentiation is usually easier to deal with mathematically because you can manipulate those things fairly easily compared to x plus iy, right? So I hope you enjoyed that and learned something from it. Okay, so you have some book suggestions for AMC 10 or 12. Elementary Number 3 by David Burton. Mathematics Can Be Fun by Perelman. Problem Solving Strategies by Arthur and Gell. Mathematical Circles, The Russian Experience by Fomin. Problems in Plane Geometry by Sharigan. Excursion Mathematics, and Principles and Techniques in Combinatorics. Okay, so I have a similar but challenging problem for you, and it says that let z1 and z2 be complex numbers such that the modulus of z1 is the modulus of z2, the modulus of z1 plus 1 is the modulus of z2 plus 1, and the modulus of z1 plus I is equal to modulus of z2 plus I. And then it's asking you to prove that z1 is equal to z2. So the complex numbers are actually equal to one another. So maybe try it out, and if you're able to do it, let me know. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.